Hope you are safe and healthy. On behalf of ISC Banner students, I welcome all participants to the third day of mathematical online camp of the year. I have great pleasure in welcoming Dr. Suresh Nayak to this platform. Dr. Nayak is currently an associate professor at ISA Bangalore. He obtained his PhD from Purdue University in 1998 with dissertation pseudo-functional behavior of cousin complexes of over formal schemes. And along with Joseph Lippmann and Ramachandra Sastry, he is the author of Variance and Duality for Cousin Complexes on formal schemes. With great honor, I welcome the professor to enlighten us on some basic ideas and results from algebraic geometry. Thank you for being here, sir. Sir will be speaking for about 60 minutes, and then we are going to reserve about 20 minutes for the questions. So please feel free to type the questions in the chat box. We'll group them and ask after the lecture.
Okay, well, what time do we start? It's 4 o'clock, right?
Yes, sir.
Okay.
And participants to be on mute unless asked, sir. So, make sure.
Can you see the screen?
Yes, sir.
Okay, good.
Excuse me, sir. So if you are ready, we can start. Students are here.
Okay, okay, fine. Okay, so thank you. So hello everyone. Uh, so I'm going to talk about algebra and geometry. So basically, this will be an introduction to some basic results in algebraic geometry, basic constructions. And what is algebra and what is geometry? We all know that in some sense. So algebra is, oops, sorry, is um, manipulation of symbols and dealing with like polynomial expressions. So for in our context, this will essentially be given by, we'll be looking at polynomial equations and some algebraic manipulations involving them. And geometry, of course, is our figures and shapes and things like that. So let's bring them together. So my basic notation will be R is for real numbers and C is for complex numbers. I assume everyone is familiar with this kind of notation, especially everyone is familiar with complex numbers. I believe people are from 11th and 12th standard onwards, so I hope everybody has seen complex numbers in some form or the other. So we'll start by looking at what we'll call as a plane algebraic curve. So consider a plane algebraic curve. So this will be a subset of R2, and it's what you would expect a curve. So it's kind of a squiggly kind of object, or a circular, or an ellipse, or one of those things. So I'll point out examples very shortly. And the main thing here is that this consists of points in R2 which are given by vanishing of one equation. And so here's your geometric object, which is defined via algebraic, which is defined algebraically, because f, which is is a polynomial in two variables, x and y. The coefficients right now we'll assume are in R, because we are looking at something which is in R2. And before we go ahead, let's also fix one terminology here. The degree of f will be also called as the degree of the curve C. So we'll say C is a curve of degree D if the defining polynomial. So of course, this is actually, okay, so sorry. There's a slight ambiguity here because sometimes a curve is not always defined by the same polynomial. So I should have been a little more careful. So we need to impose some additional hypothesis on f to make sure it's well defined. But okay, we'll be a bit loose here, and we'll never have the reason to. There'll not be any ambiguity. So in our given situation, it'll be clear what we mean. So we'll continue with this slightly loosely defined degree of C. We'll just say it's the degree of the polynomial defining it. Okay, so what are examples? These are your familiar examples. So a line, for example, circle, ellipse, parabola, hyperbola. I'm sure all of you have read about these things. So a line is given by this equation, and this is how it looks. Circle, I've just written some generic equations for them. This is not the most general form. You can translate these things, and in case of ellipse, you can also rotate them, and so you get slightly different looking equations. And here's a very special, very specific kind of parabola I've written here. And okay, this is not so well drawn. This is your hyperbola here. And some slightly higher degree polynomials. So let's come back to the degree. The degree is defined to be the sum total of all the degrees of the variables occurring in the equation. So there are more than one variables occurring here. In fact, two variables. So you add up the degree of all the variables occurring in each term. So this is one term. And here the x is the only variable. So the degree is one. And this is actually a degree 0 term. But the maximum of all the degrees is 1. So this is a degree 1 polynomial. Similarly, this is a degree 2 because these terms are degree 2, 2, and 0. This is again degree 2, 2, 0, 1, 2. And this case, the total degree is 2 because x has degree 1 and y has degree 1. So And here I forgot, but I mean, typically the right-hand side, we consistently allow it to be 0, but we'll be a bit loose and sometimes we'll bring the constant on the other side. So this should have been xy minus 1 equal to 0. But anyway, that's equivalent to this. So this is again a degree 2 thing. And so here, this is y square minus x cubed plus x is equal to 0. This is going to be a degree 3 curve because this term has degree 3 here. And its locus, one can show, looks roughly like this. You vary the terms and coefficients a little bit. So instead of x, if I put x squared here, then you can show that suddenly there's a sharp point here. And if you put y squared minus x cubed here, in fact, it becomes a really sharp point. Sorry, this was not a sharp point. This was a crossing point here. And y squared minus x cubed is equal to 0, gives you a sharp point here. And some higher degree equation is giving you a curve which almost starts resembling a square, but with some rounded edges here. All right, so these are your, okay, yeah, this extra slide is just to say that the degrees are 1, 2, 2, 3, and 4. So these are the degrees of these curves. Okay, so geometrically, we can ask, what does the degree signify? I mean, right now we have defined degree as an algebraic thing. I mean, you look at the equation and look at its degree, and then that's your degree of the curve. But what would it geometrically signify? And it turns out, if you stare at it a little bit, you'll start suspecting what the answer is. So let me just give that. And that is basically one should try to intersect these curves with lines. And when you intersect these curves with lines, you'll see what's happening. So let's go to the next slide. And I have intersected each of these curves with suitable lines. So the same examples. Here I have this line. I cut it with another line. I get exactly 1 point. Circle, I'm cutting it to the line. I'm getting 2 points. Ellipse, 2 points. Parabola, 2 points. Hyperbola, 2 points. And they are all degree 2 curves. And then this cubic here, I draw this line and it's cutting in 3 points and 3 points here and 3 points here. So, and these were all cubics. But in the case of degree 4, I do run into a bit of trouble. I'm not able to get a line cutting it in 4 points. And in fact, you would in fact go back and object that this could have been the situation in all these cases also. Because, for example, I could have drawn these lines slightly differently, and then I don't really get these numbers that I've written here. So in fact, let's choose some other lines. So for example, in this case, I could draw a parallel line. For a circle, I could have drawn a tangential line. So there's only one intersection, 0 intersections, and here also 0. And here I draw a vertical line. So I'm assuming, yeah, this is the parabola. So again, just one intersection, no intersections of hyperbola. Here you have cubics and only one intersection seems to be here, and here also only 2 intersections, and here no intersections. So really, these numbers are not necessarily indicative of all possible intersections of lines to them. But what you would notice is that these numbers are sort of an upper bound. I mean, yes, it's true that I got only 2 intersections here, but if I slanted this line a little bit, I would have gotten 3. And similarly, I perturbed this line a little bit, I would have gotten 3 here, I would have gotten 3 here. But it seems hard to go beyond 3 in all these 3 cases, and beyond 2 in all these conics. And you can never really get one here, more than 1 here in the case of line. So certainly these numbers are giving you some sort of an upper bound. And so then that's the question that gives rise to, that we arrive at. So here's a question. Here's a more general question. Given 2 plane algebraic curves, C and D, of degrees m and n. So above, what was happening was one of them was, let's say, a curve of degree 1, 2, 3, or 4, and D was a line. So n was 1 and m was from 1, 2, 3, and 4. So given 2 such plane curves, how many points of intersections do they have? And the sort of guess that we looked at is more generally here's the answer. One can prove it's not so difficult, but also not that easy that I can prove it in this lecture. So I won't do that. So one can prove that it is at most mn. So m times n. So the number of intersection points of these two curves C and D is at the most m times n. And so if n is 1, then it's the number of points of C with any line is at the most m, and where m is the degree of the curve. And so that gives you sort of one possible interpretation of the degree. It's the maximum number of points you could have by intersecting into the line. Though if you go back to one of those examples, the quadratic, you would say that, okay, well, I mean, in this case, actually, you never really achieve it. And indeed, that is true. So there is obviously, while this result is giving us upper bound, many aspects of this results are somewhat unsatisfactory, and in particular, this inequality is unsatisfactory in some sense. So we would like to improve it. And so here's the question: what is preventing this equality from happening, and how do we interpret this deficit, and how do we incorporate it? Meaning, how do we sort of handle it and try to find a way in which we can get an inequality, replace this inequality by an equality. So I would like to get to the situation where I can say that C intersection D has exactly mn points. So we have already seen examples where it doesn't happen. So what we have to now really do is analyze further what is happening in those situations, and then we will try to come back and give a better statement. So that's what I will now do. Okay. So I don't know. The format of these lectures is such that I guess the questions will be towards the end, I suppose. But if anybody has any urgent clarification or something, I guess you could still send a message or interrupt. It's okay. All right. So let's come back to the situation. What I have is a conic here. This is my parabola, y equal to x square. And what I'm now trying to do is draw different lines which are giving me different intersection points. So this one is giving me 2, this one is giving me 1, and this one is not intersecting at all. And so I want to understand what is happening here. Okay, so to do that, let's start with a somewhat generic situation. And the generic situation would be to draw an arbitrary line. So take an arbitrary line and cut it with the parabola. And let's see what the points of intersection will be. So to find points of intersection, so how do we find the points of intersection? Basically, we simultaneously solve for the two equations. One is the equation of the parabola, and one is the equation of the line. So the equation of the parabola is y equal to x squared, and the equation of the line is y equal to mx plus c. And so, of course, when you when you are trying to simultaneously solve for these two equations, you will immediately notice that these are both y. So you can put this equal to this. And that gives you this equation, a quadratic equation purely in x squared minus mx minus c. Here, m and c are some fixed constants, but unknown. So, not unknown. I mean, this is, never mind. These are constants where we shall vary m and c depending on how we want this line to look like. This will take care of almost all lines, but, well, not every line, but almost all lines. So, by trying to solve these two equations, we have arrived at this equation. This is a quadratic. We can immediately solve for x. And once we know x, then of course we also have y, because y is given by y equal to x squared. So knowing x immediately uniquely determines y. So everything just boils down to knowing what is x, and that boils down to this quadratic equation. And then, as we all know, this quadratic equation, the only there's an explicit formula, so we can of course solve for it. But the only problem is two things. One is that it may have equal roots if the discriminant is 0, or worse, if the discriminant is negative, it may even have complex roots. And if the x is complex, then y is also complex, and so you don't really have a point of intersection. And that is what is really happening, for example, with this line where y is negative. So this is y is y, so m you can assume is 0 and c is a negative number. And so what you have is x square plus a negative number is equal to 0. And so therefore that is giving you a complex root. So indeed, it's the presence of these complex roots which is creating problems for these intersections. And so therefore, if we want to come back to this earlier result about getting a better statement about the number of intersection points, what this is suggesting is that we should expand our domain, or rather the environment in which we are working. And instead of looking at real numbers, we should perhaps start working with complex numbers. And so that is our first remedy for getting a better theorem. We should allow complex values for x and y. And what does that mean? That means we will look at points. I mean, instead of looking at points in R2, so we were looking at a comma b in R2 such that f of ab is equal to 0. So instead of doing that, we will replace r by c, complex numbers. So these are all numbers. Again, I assume that all of you are familiar with complex numbers, all numbers of the form a plus ib, where I is square root of -1. So this is your this is complex 2 space, so complex cross complex, so all ordered pairs of complex numbers here. So instead of R2, we'll look at C2. Now C itself, we are familiar of thinking of C as a real plane. So geometrically, this actually starts looking like R4. And so that's a slight drawback. So indeed, I'll say something about it immediately again. So therefore, once we start looking for complex values of x and y, our curves have to be then thought of as pairs a comma b in C2 such that f of ab is 0. And so we are calling them curves, but really we should be careful because they may not actually look like curves. So they are more, well, sort of complicated objects, or maybe larger dimensional objects in some sense. But because algebraically they are still given by one equation in two variables, we will think of them as complex curves. So we'll call them as complex curves. And now that we have generalized our definitions, we may also allow f to have complex coefficients, though I will not really look at such examples in this lecture. In general, it's just a natural way of extending these things. So there's nothing special or peculiar about using. Once we have come to this situation, even the coefficients, you can allow them to be complex, and you still have what you can call as an algebraic curve. But you should be careful and call it a complex algebraic curve. And one reason why one should be careful is that a complex line, if somebody gave you an equation like this, even if say a, b, c are nice real numbers, or let's say a, b, c is 1, then x plus y plus 1 equal to 0. If I wrote down the solutions of this in the real plane R2, you will get a real line. You'll get the line x plus y is equal to -1. So it's a line of slope -1. But if I said that now instead of looking at all real solutions of x and y, look at all the complex numbers x and y, look at all complex pairs x and y such that ax plus by plus c is equal to 0. Then that set, it's not hard to see, is in fact looking more like a real plane, because here's one way to think about it. Okay, let's pretend that, let's take a specific equation. So let me go somewhere on the side here. And let's take, for example, x plus y plus 1 is equal to 0. This is one, for example, one such equation. And what we see is that if you give me any value of x, then the value of y is uniquely determined. And conversely, the value of y is uniquely determined. So in some sense, you can project this line to just the x coordinate or the y coordinate, and that gives you a one-to-one correspondence. So let's see, x plus y. So in R2, so this is, I am in R2 here, and this is x plus y plus 1 equal to 0. This is my line like this. And what I do is I project it down to this to this maybe x-axis or y-axis. Sorry, this is the x-axis. And then I'll get a one-to-one correspondence. I mean, a point here corresponds to a point here. And that sort of tells me how to go back and forth between these two things. And in particular, this is an algebraic way of, well, I mean, I'm saying it algebraic, though I've drawn it geometrically, but it just means projected to the x-coordinate. It's an algebraic way of telling me that this is looks very much like this, which is a line. Now, if you extend this idea to the complex situation where A, B, C are, if you want, still 1, 1, 1, but now I'm allowing x, y to be complex numbers, then again, you will see that for any value of x, you have a unique value of y. And so you project it to, let's say, the x coordinate, and that gives you a 1, 1 correspondence between points on this locus and the points, the values that x is taking. But if x is allowed to take complex numbers, then you will see that there's a one-to-one correspondence between the locus of this and the complex plane. And so it's more natural to think of this complex line as actually a real plane R2. But algebraically, it is still given by this nice linear equation. And therefore, there are also good reasons, and this is a very confusing situation, I agree, but there are also good reasons to think of it as a complex line. So we will. This is a bit of a ambiguous terminology, but we will live with that. So this is a complex line, which geometrically is closer to looking like a real plane, but however, we'll still call it a complex line. So with this situation, we will go back to our familiar curves, and we can try to, instead of looking at only the real points, we can try to look at the complex points. And when we do that, we can try to hope to get a better theorem. So that is our first remedy. And indeed, that takes care of, let's come back here. It takes care of several lines here. For example, it will take care of certainly all such lines here which don't seem to intersect the parabola at all. They will all have complex solutions, complex intersection points with this parabola. So if we are only drawing the real points here, and that's why we are not seeing the intersection. So if we were to keep track of all the complex points of both the parabola and the lines, then we will certainly see that they have an intersection. So that sort of gives.
Hello,
yes. Yeah, go ahead.
Sir, can I ask a question?
Sure.
Sir, I mean, when we are checking for the, I mean, when we are drawing it in complex plane, I mean, when we are allowing x and y to be complex, then
yes,
the picture that we are drawing, I mean, what we are considering to be the coordinate axis.
No, we are not. First, we will not draw. The coordinate axis will be C cross C. So there will be no, we won't really draw because this is R4 and we really cannot draw. So, but we will only handle these things algebraically, which means we will think of first coordinate as one complex coordinate and the second, first term as one complex coordinate and second term as another complex coordinate. That's the best we can do. No further pictures can be drawn.
Okay.
Yeah. Okay.
Sir, I have another question.
Yeah, sure.
What would a parabola look in the C cross C?
I'll come to that. It will essentially look like a punctured sphere. I'll come to that, but I will not really prove that. I'll more or less state it as a fact. But it's not hard to show that the parabola, if you look at the complex points, then it is actually after some sort of continuous deformations, if you like, or whatever. It actually looks like, geometrically, it looks like a sphere with one point missing. And we'll come to that missing point very soon. Okay. I'm not going to prove that part, but yeah, we'll come to that. Okay, so let me move on now. So here I have, so we have done the first remedy, which is to expand our environment in which we are working, and so start working with complex points. That's the first thing. Now comes the second thing, which we will actually sort of slur over because we will not, it's a little more technical to describe it too precisely, but I'll just briefly mention it. So here's the line in question, which is again a problematic line because this is your parabola, this is your line, and if you solve for them simultaneously together, you see that these two are equal, so x square has to be 0, and this is your quadratic equation which has equal roots. So you're getting only one solution for x, and that's the problem here. So this line is cutting it exactly this point here. So here the peculiar situation that is geometrically happening is that this is actually the tangent line. And tangent lines will always have this behavior. The intersection numbers will always drop whenever your line becomes a tangent line. And somehow the intuitive idea is that, I mean, okay, forget this complex part here. Pretend that this complex part was not really there. If you are just looking at lines here, you were really getting a secant here, and there were 2 points here. And as your line starts coming closer down and down, these 2 points become equal. And so these 2 points have, I mean, of course, that is what is happening with quadratic equations also. So these 2 points have really come close together each other. So there is no really resolution of this matter except for declaring that this being a tangent line, we will say that there is intersection multiplicity, higher intersection multiplicity at the point of contact. So the intersection number at this point of contact is not 1. You have to introduce extra number here. And in this case of parabola, the multiplicity we will declare it to be 2. So of course, this does look a bit silly or a cheating kind of solution, but this is the best we can do. And it turns out these are not so silly after all. This way of assigning the intersection numbers are not always 2, so it can be more. It's more than 1, but it can be much more. And there's a precise way in which they can be measured. And once you start figuring out what it is and start using it, you can get more interesting things. So for curves, these multiplicities, as I said before, I'm not going to tell you how to calculate them. Maybe I'll just orally say something about it. For curves, these multiplicities are calculated locally. This whole thing is a local calculation because it's a very local phenomenon. Just what is happening in the neighborhood of this point. And what is happening far away is not really relevant here. And so near the point of contact. And the intuitive idea is that if the two curves have distinct tangent lines, then the multiplicity should be 1. And this is sort of like what we would call a transversal intersection. And if the two curves seem to share a tangent line, then the intersection multiplicity should be greater than 1. And the exact definition of the multiplicity is a little more technical. It can be defined easily if one does a little bit of algebra, but we will not do it right now. But I'll just maybe I'll very briefly say it has something to do with looking at your equations, the equations that you have, and seeing to what extent you can manipulate these equations and generate all possible functions in a neighborhood of this point. And the failure to generate meaning, look at, so here the equations are y minus x square and y. So those are the two equations. So let me write. So y minus x square and y. These are your two equations. And the idea is to somehow look at these two equations and all possible combinations of these two equations. So you are allowed to multiply. This polynomial is anyway going to be 0 on the parabola, and this y is going to be 0 on this. So both of these are 0 on the intersection points also. And any multiple of this will also be 0. And so the idea is to look at all possible multiples and combinations of these functions and try to see to what extent you can generate, you can get various functions in a neighborhood of this point. And your failure to get all possible functions can be measured by seeing how many functions you are not able to sort of generate using these two. And but of course, you have to be a bit careful about that. Some independence has to be measured there. And once you have that, then you can give a precise definition of this intersection multiplicity. So it involves some algebraic manipulations, but I will not get into that. So let's skip that for the time being and just take it as an intuitive thing here. Just saying that the intersection multiplicity is always greater than 1 at a tangential point of contact, but at such a transversal point of contact, it's always equal to 1. And if they don't meet, then of course the intersection multiplicity is 0 at any given point on any of the curves. So this is how one can try to remedy the situation a little bit. And so that is the second remedy. And now here comes the third one. And that had to do with this particular line here. So I have a parabola here. Now this line was not captured by saying y equal to mx plus b because this is a vertical line. And it's certainly not tangential. So the intersection multiplicity, it's intersecting at one place, but somehow the other point seems to be missing here. And one clue to that other point missing is to start looking at the tangent lines of this parabola here. And you will see that the tangent lines of this parabola, as you go up this parabola, they are becoming more and more vertical. Their slopes are increasing. You can calculate, if you have done some calculus, you can differentiate x squared. This is the graph of x squared, and the derivative of x squared is 2x. And that is the slope at any given value of x. So as your x increases, the slope of this line is increasing. So anyway, you can also pictorially see here, geometrically, you can see here that as the parabola increases, the slope of the tangent line is increasing. And that seems to suggest that as the parabola increases, as you go up the parabola, it's becoming more and more vertical in nature. Okay, why am I saying that? Well, there's an analogous situation which we have ignored, in fact. You didn't even have to go to the parabola. You could have just taken two parallel lines. And these two parallel lines don't seem to meet at all. So degree one, the expected intersection multiplicity is 1, but they are parallel, so there is no intersection. All right, so with this situation, the next remedy is to therefore introduce a point at infinity for every set of parallel directions. So for all these parallel lines of a particular slope, I'll introduce one point at infinity here. For all vertical parallel lines, I'll introduce one point at infinity somewhere, at infinity. So this is a vague phrase. I'll try to make it a bit more precise by some abstract method. So I hope you will be able to get something out of it. And therefore, the intuitive idea is that this parabola is becoming more and more vertical. So this parabola is approaching this vertical point at infinity. And this vertical line is also going to pass through the vertical line at infinity. So in some sense, this parabola and this line should meet at the vertical point at infinity. So once I am done with introducing points at infinity in various directions, one in this direction, one in this direction, one in this direction, and one vertically, then I should be able to say that this parabola here and this line here will intersect or will meet at the point at infinity. All right, so that's what I'm going to do now. So that's the third remedy. Introduce a point at infinity along each direction. Or, well, this is a slightly vague phrase because direction can mean one direction this way and one direction this way. So, but unfortunately, the way the algebraic process is done, which I'll do it shortly, for this entire line, there will be only one point at infinity. So there is, for example, vertically, there's nothing, there is only one point at infinity. You can either call it up here or you can call it down here, but they are identified. So the up point at infinity and down point of infinity are the same in some sense. So that is how I'm going to do that. I'm going to, for every line, I'm going to introduce one point at infinity. And this idea actually comes from perspective drawing. So yeah, I actually meant to introduce some pictures here, but I forgot. So if you have learned a little bit, or you can just Google this. If you learned a little bit of perspective drawing, basically trying to draw three-dimensional rectangular objects or cuboidal objects on a plane, you will, or if you just want to draw, let's say, an infinite railroad, then the most realistic picture is to draw it like this. Let's see. Yeah. And then you put maybe line here and then the line here. Okay, I'm not drawing very precisely, but carefully. But it's best to draw them as if these lines are converging somewhere. I mean, if you just draw two parallel lines and then draw it like this, it doesn't give you the feeling that this is a three-dimensional picture. But this gives you a slightly better feeling, I hope. And similarly, one can talk about drawing cuboidal or buildings. If you just look at any picture of various buildings, you will notice that the various edges of the buildings, they parallel edges, so-called parallel edges, when they are represented in the two-dimensional plane, they don't really look parallel. So they seem to go somewhere and meet at some point at infinity. So that is the idea that came from perspective drawing, and then it was mathematically implemented by as follows. So this is how you do it. Basically, you take any line. So here's a line through the origin. I'll take a line through the origin. So that will be representative of one direction. So one line through the origin will correspond to one direction. So this line, let's say, is passing through the point A, comma B. Of course, it also passes through 2A, comma 2B. It also passes through minus A, minus B. So for all these points, there is one point at infinity, and this is the point at infinity. And similarly, there are other lines. So there'll be a point at infinity here. For the vertical line, there's a point at infinity here. For the horizontal line, there's a point at infinity here, and so on and so forth. So there you have this entire horizon of points at infinity, which I'll call it as H infinity. And I need a good notation for writing these points at infinity. So the point at infinity along the line, let's say this line, I'll represent it as TA, TB, where T belongs to R. So by varying T, I'll get different points in this line from the origin. Maybe one can call this point at infinity as infinity times A and infinity times B, because I mean, that's what has happened here. I've just let T go to infinity. But keep in mind that these A and B are not unique, because A and B could have been minus A minus B also. It could have been 2A 2B also. So really, I shouldn't use infinity A, infinity B. Better notation would be to use a ratio, infinity A. So of course, right now we are arguing only informally, because we are just still sort of debating about what's a good notation. But right now, what we'll say is that this note, it's better to think of this as a ratio. So we'll call it as infinity A ratio infinity B. So I'll use this colon here. That's the ratio. And of course, I'm not very happy about this infinity symbol. So I'll think of infinity as 1 over 0. So I'm almost there. I can think of this as A over 0 ratio B over 0, which is still not a good notation because I have 0 in the denominator. So I just went from here to here. And so one good notation, it turns out, is to just bring this. So these are also, already we were looking at one ratio here. And now each of these terms also seems to have another ratio. So I bring that ratio term, the denominator term on this side. And now I think of this as a simultaneous ratio of three numbers, in which the third number is playing the role of getting divided by in some sense. And then it is sort of like looking at A over 0, B over 0, which is like infinity A, infinity B. So this notation is better because now there are no problematic symbols here. Everything is an honest number, real number here. I have used this ratio symbol here, so this colon here, and that will be our symbol for the point at infinity for this line here. So that is our point at infinity, A colon B colon 0, or A ratio B ratio 0. This is simultaneous ratio of these three numbers. But what happens is now you have two sets of notation. One notation for your normal ordinary points, and one notation for your fancy, this newly introduced points at infinity. So to bring everything together, what one can do is, anyway, since we thought of as 0 as something which was getting divided here, think of A comma B as A colon B colon 1. And basically you are just divided by 1. And so that is this point here. So this is A comma B comma 1 with scaling factor. Okay, here maybe this is confusing. I'm not sure. This is not the same. So this point 2A 2B will be 2A 2B 1. Whereas now that I have decided that I can divide by the third coordinate, A colon B colon 1 can also be thought of as simultaneous ratio of 2A 2B 2. So keep in mind that there is a 2 here. And therefore, this 2 can be cancelled. Anything which is a common factor can be cancelled. You can, and once you bring it to the third coordinate to 1, you can then sort of drop it, and that becomes your ordinary point. So now I have a common notation for all points, the points at infinity, which is the points on the horizon, and our ordinary points a comma b. So ordinary points a comma b. So here's my summary. An ordinary point a comma b is now written as a over 1 and b over 1. So a colon b colon 1. And if you want, you can also think of it as lambda a over lambda, which is again a, comma lambda b over lambda, which is again b. So I'll just think of it as this, or which is the same as this for any lambda you like, as long as it's not 0. And a point at infinity for a line, TATB for this particular line, is the point A, B, 0. So the big difference is that the third coordinate here is non-zero. You can make it any non-zero number you like. Here it is 0. And these are your points at infinity. So this is the new idea. This what we have done is we have taken the real plane, ordinary real plane, and added one horizon. So added infinitely many points on the horizon, each along one line. So for every line, there's a point here. I hope, I mean, I don't know how much, I mean, this this is called projective geometry, and this actually requires 1 or 2 lectures on its own. So I'm just trying to condense it and give you an intuitive idea of what it looks like. I hope you are able to get something out of this. So let's now make the definition. So we'll now look at the set of all such points A, B, A colon B colon C. And to be very precise, if you want to define them in a very precise way, you should think of them as equivalence classes of this relation. So I don't know, I think in 11th or 12th you do sets and relations. So introduce this relation. A, B, C, you say is equivalent to 2A, 2B, 2C, or 3A, 3B, 3C, or whatever. Lambda A, lambda B, lambda C, where lambda, or lambda should have been, lambda is not 0. And the only thing which is not allowed is all 3 coordinates being 0. All 3 coordinates being 0 was not happening here or here. And we will not allow it here also. So that is the only thing which is, because that actually will have no meaning in this particular situation that we are trying to do. So we will not allow that point. So that is the only thing which we are not allowing. And all other triples up to simultaneous scalar multiplication, we'll identify them. When we identify them, we'll write them as simultaneous ratios like this, A colon B colon C. And this collection of points will be called the real projective plane. So we'll denote it as RP2, P is for projective, and we'll call it as real projective plane. And what is the real projective plane? So the same summary that I given here in this terms of this definition here can now be described as follows. If C is not 0 in my points ABC, then A colon B colon C is, I can divide by C, and I get, it's the same as A over C colon B over C colon 1. And once I made this 1, I can try to drop this, and then it corresponds to the ordinary point A over C and B over C in R2. So these kind of points with C not equal to 0 will be ordinary points. And when C is equal to 0, I get a point at infinity. This is A colon B colon 0. It's viewed as a point at infinity in the horizon for the line TATB. For the line TATB, it's A colon B colon 0. So since these two cases exhaust all of RP2, so I can now think of RP2 as, so real projective plane as R2, my ordinary usual plane that I was familiar with, all of us were familiar with till 1 hour ago, union this new horizon that we have introduced, horizon, this points at infinity. So RP2 is R2 union this points at infinity. So that is the new thing we have introduced. And why did we do this? We have done this so that we can now think of curves as meeting at infinity. Of course, not all curves will meet at infinity, so we have to find a way of describing when do curves meet at infinity. But before that, let me mention one more thing, which is that whatever we did here was a very algebraic process. Even though I actually drew pictures here, and I made a horizon at infinity, etc., you can completely ignore this picture and you can start from here. Of course, if you did that, you will not really understand why we did this. But mathematically speaking, you can always start from here. You can always do something like this. And when you do something like this, you will see that there's nothing peculiar about real numbers. You can put any other thing also. For example, you can put complex numbers. In that case, again, you'll have this problem of not being able to draw pictures, not being able to pictorially interpret exactly what has happened. Yes, that's a problem. So please bear with me. There is no convenient or neat interpretation of what has really happened in geometric terms. But in algebraic terms, we can sort of still use the same kind of language and say that I can, if I, everywhere, wherever there was R, if I replace it by C, I can get a similar construction. And CP2, which will again be, what will be CP2? CP2 will be all triples of complex numbers, which is equivalence classes where lambda is in C minus 0, so non-zero complex numbers on C3 minus 0, 0. So you look at all such triples. That will be a CP2. And CP2 will again be a union of
Hello,
the
sir.
usual C2. Yeah, and usual points at infinity. Yes, please.
Sir, I mean, given a equivalence class, the plane that
Yeah.
we consider there, each point refers to the particular A by C, comma B by C points, right? I mean, given a triplet ABC, I mean, in the equivalence class, for all of them, the A by C and B by C, these are the same. So that actually denotes one point in the plane, right? I mean, the set of all points by point
Yes,
with
this
finite.
denotes 1 point in the plane. Correct. Yes.
Okay.
You can talk about A by C and B by C provided C is not 0. That's the point. That's the thing.
Okay, sir.
Yeah. So very, very vaguely speaking, what we have done is we started with R2. Then we introduced one extra coordinate. And so we seem to have gone to a higher dimension. But then we cut down the dimension by introducing this relation. This relation, in some sense, cuts down the relation because cuts down the dimension. But in doing so, we have come back to two-dimensional object. But this two-dimensional object has a few surplus points. And that few surplus points is when C is equal to 0. The C equal to 0 are the surplus points. Those are the points at the horizon, the points at infinity. That is our main accomplishment here. And so you can do this algebraically. So you can do this for complex numbers also. Okay, I don't know how much you're following, all of you, but I hope you have vaguely understood that there are some points at infinity we have introduced. And now I would like to point out that there's a simple way of actually finding out what these points of infinity are. And once you realize that, then you can actually see what is happening with the intersections. So what are points of infinity of the parabola y minus x squared? This is our honest parabola in the real plane. But I want to know what is its point of infinity. And I had already hinted for that the tangent line is becoming vertical. So it should somehow go and meet at the vertical point at infinity. Let's see if that can be seen. Now, our usual points will be A, comma B. But now I'm interested in going to the real projective space. So to go to the real projective space and find out what are the extra points there, what I'll do is I will think of y as capital Y or capital Z and x as capital X or capital Z. So that's because our, if you go back to our formula here, where is it? Yeah, I mean, A over C and B over C. This is what, I mean, A, B, C should be thought of as A over C and B over C, provided C was not 0. And so if given 2 points here, if I want to go back here, I mean, in some sense, that's what I'm doing. I can multiply by something. I can multiply by any C here, and then I can, well, I mean, if you know what is C, I can go back here. So roughly speaking, this kind of going from here to here, okay, going from here to here is less ambiguous. So going from here to here, this process hints that what we should do is we should put little y is equal to capital Y over Z, little x is equal to capital X over Z, and see what we get. So this is the equation I will get. Little y, I've put it as capital Y over Z, little x as capital X over Z, and I get this equation. Of course, I clear off the denominators, and this is the equation I got. So now if I solve for all the complex, no, sorry, forget the complex. Let's right now stick to real only. We'll come back to complex later. So if I solve for all the solutions of this, I'll get triples. And in that triple, when I divide it by the third coordinate, I will get back my original points. Notice here that this was not a homogeneous polynomial. This polynomial had mixed degrees. There was a degree 1 and degree 2 term here. But this polynomial has degree 2 and 1 plus 1, degree 2. So both of them are degree 2. So this is called a homogeneous polynomial. And this is what will always happen. When you do this kind of process, you will get a homogeneous polynomial. And now, if you put z not equal to 0, then you can divide by z, and you can go back, and you can get these points, y comma x. Those will be your usual ordinary points of your parabola, the finite points. Those on y equal to x square. But when you put z equal to 0, those are your points at infinity of this parabola. So I hope the recipe or the procedure is very straightforward. Start with your equation, substitute y is equal to capital Y over z, x is equal to capital X over z, and then readjust your equation and see what you get. And then put z equal to 0 to get your points at infinity. If z is not 0, you will recover your usual ordinary points. So now if you put z equal to 0, what you will see is x is 0. And we have already said that y is not allowed. I mean, all three coordinates cannot be 0. X, y, and z. So if x and z are already 0, then y is not allowed to be 0 because all three coordinates should not be 0. So y has to be non-zero. But when y is not 0, it is any point 0, b 0, which would a priori seem like infinitely many points. But remember, this is an equivalence class. So you can simultaneously divide or multiply by any particular number. And so you can divide by b itself because b is not 0. And so you get 0, 1, 0. So which means that really there's only one point. And what is that point? That is the point 0, 1, 0. And if we go back to how we are looking at things, this is the point at infinity for the multiples of the point 0, 1. 0, 1 is a point somewhere here, and all multiples of that is this line here, and this is the point at infinity of that line. So this is the vertical point at infinity, and we have now seen that the parabola actually is going to pass through this vertical point at infinity. Another thing that, yeah, go ahead.
Yes, so there.
Ayan Ghosh has raised.
Ayan has raised his.
Sorry, there's an echo or two people are speaking.
Sorry, I didn't mean to raise my hand.
Okay, one of you can speak then.
Yes, sir. No, sir. Actually, I wanted to tell that somebody was raising.
Oh, okay.
Okay. Thank you, sir.
Okay, thanks. Okay. Yeah. So therefore, what we have is start with this usual parabola, and then this process of substituting capital Y over Z, capital X over Z is called homogenization, and you get a homogeneous polynomial. And then from here, you can get back here by a simple thing, either divide by Z square, Z to the power degree of this polynomial. Degree is 2, so divide by Z square. And then you'll get Y by Z minus X by Z whole square, which is little y minus little x. Or you just substitute Z equal to 1 and replace capital Y and capital X by little y and little x. That will also give you the same thing. So there are different ways of describing the dehomogenization process and the homogenization process. And the net result is that the parabola has a point at infinity. Okay, so I think we are slightly running out of time. So let me, let's look at a few more examples. Hyperbola y square minus x square is equal to 1. Again, let's do the same process. I'll repeat the process. I'll substitute x equal to capital X by Z, y is equal to capital Y by Z. This equation becomes this. Clear of the denominators, you get y square minus x square is equal to z square. Z not equal to 0 will give you ordinary points on the hyperbola. And z equal to 0 will give you, well, when I say ordinary points, I mean the third coordinate will be some non-zero value of z, and then you have to divide by that and then eliminate the third coordinate, and you'll get the first two coordinates, and those will be your points on the hyperbola. And if you put z equal to 0, you will get from this equation y square minus x square is equal to 0, which means y is equal to plus or minus x. Again, x cannot be 0 because if x is 0, then y will also be 0 and z is already 0. So all three will be 0, which is not allowed. So x is not 0. So you can choose any non-zero value of x. I'll call it as 1. Then y is either plus 1 or minus 1. So y is plus or minus 1 and 0. And these are the only points because whatever non-zero value you put here, you can divide by it. You can simultaneously divide by any particular coordinate. So not necessarily the third coordinate, by second coordinate first, or any number. You can simultaneously divide by any number. So in particular, you can divide by the first coordinate and then ensure it is 1. So if this is 1, then we know that this is 1 or minus 1. So there are 2 points at infinity. And what are these 2 points? One is along the direction 1 is to 1, which is y equal to x. So it's in this direction. And the other one is in the direction along 1:1:-1, which is the line y equal to minus x, and that is this point at infinity. So those are the 2 points at infinity. You can see that these are the asymptotes of the hyperbola. And so the asymptotic directions of the hyperbola are where the points at infinity are lying. And that was sort of what is happening with the parabola also. There, of course, there's no asymptote, so to speak, but the tangent lines were becoming horizontal. Here, the tangent lines are, as you can see, are becoming more in this direction and more in this direction here. Even a much simpler situation is just an ordinary line, y equal to mx plus c. You homogenize it. I mean, substitute y is equal to capital Y by z, little x equal to capital X by z. You'll get this equation. Again, z not equal to 0 will give you back the original points. Z equal to 0 will give you the new points at infinity. And what are the new points at infinity? If you put z equal to 0, you get y equal to mx. Again, they both cannot be 0, so neither of them can be 0. So you put x equal to 1, and that will be enough. And that will tell you y equal to m. So you get 1:m:0. But what does that tell you? That tells you something interesting. The value of c was not important. The value c doesn't play a role here at all, which is in fact what was one of the motivations for this. So all parallel lines, y equal to mx plus c1 and y equal to mx plus c2, they will all, when you extend them to the projective plane, they will all meet at this point at infinity, 1:m. They all meet at infinity. So all parallel lines meet at infinity. That was in fact the motivation behind this thing. And it's nice to see that our construction is actually doing that. And so now let's make a few definitions. A projective line in RP2, or for example, CP2, we'll call it a complex projective line, or here we'll call it a real projective line, is a set of zeros of a linear equation, ax plus by plus cz. So you just put ax plus by plus cz equal to 0. And then you get look at all the solutions and look at the simultaneous triples. Maybe I should have used some other. Maybe I should have called them alpha, beta, gamma. And then look at the solutions of this, and those solutions will give you some triples in RP2, and those are your that is the projective line. We'll assume that at least one of the ABCs is non-zero, so that this is a non-zero equation. So almost all projective lines in projective plane can be viewed as an ordinary line in the ordinary plane together with its point at infinity. So every line has a point at infinity. If you put that together, you will get a projective line. This is not hard to see. It's very easy exercise. And the only exception will be the line z equal to 0. So if A and B are 0, then you're left with the equation z. And so the 0 locus of z is z equal to 0. And that line, however, has no intersection with the ordinary plane. And it lies completely outside the ordinary plane. It is in fact the horizon. The horizon is also a line, actually. So that is called the line. So it's sometimes called as a line at infinity. So we can call it the horizon, or we can just call it the line at infinity. And that is basically all the points where the third coordinate is 0. So an easy exercise of what we have accomplished is that, based on what we have accomplished, is that any two distinct projective lines meet at a unique point. So no exceptions whatsoever. In the ordinary plane, you have to make an exception, say two non-parallel lines. So now that distinction can be removed. And so any two distinct lines intersect. And so more generally, instead of lines, I can look at a plane curve. So a projective plane curve in RP2 or CP2 is a zero set of a polynomial f, where fxyz is a homogeneous. So we will always work with homogeneous polynomials when we are dealing with projective space. Homogeneous non-zero polynomial of some particular degree, the degree will vary, with coefficients coming from R or C. So if you want to work in RP2, you'll use R. If you want to work with CP2, you can use C. Or even if you work with R, you can still look at the corresponding complex points, which is what we have to do with the parabolas and all. And so then we have the following theorem. I forgot to mention the name. It's usually called as Bezos Theorem. And so this theorem says that if you have two curves in CP2, which means these are two non-zero polynomials, homogeneous polynomials of some degree m and n, let's say, whatever. So if they are in CP2, now this important part is I have no longer put RP2. Now here you have to put CP2, and F and G have no common factor. Unfortunately, that is one condition you have to put. Then their intersection has exactly what you expect, degree F times degree G points, counting multiplicities. So provided you are counting multiplicities, that's the other thing. So we have basically now what we have done is we have extended our definitions, modified our definitions, and in the process obtained some new things like maybe we should work with complex, maybe we should add points at infinity, maybe we should use multiplicities. And when we do that, we get a precise theorem. The only extra hypothesis I have to add is that they have no common factor. If they have a common factor, they will have infinitely many solutions in common that can be shown. So basically, because every polynomial has infinitely many solutions, so a common factor will give you, oops, sorry. I pressed the wrong button. Okay, I think now I'm okay. So if they have a common solution, sorry, what was I saying? Yeah, if they have a common factor, then there will be infinitely many solutions. So we have to discard that situation. For example, if you put xy equal to 0, that is one polynomial, and that will have two solutions. X equal to 0 is the y-axis, and y equal to 0 is the x-axis. You can homogenize it, but you will still get two lines with some points at infinity. And similar, but then I can also look at some other equation which will give me maybe the x-axis together with some other vertical line. And so the intersection of these two will turn out to be this entire x-axis. And so that you cannot escape. So right now, so this is, but in some sense, this is a satisfactory theorem. It's not a very deep theorem. It's not, I mean, one can prove it in first basic course in algebraic geometry. But it's interesting, it's not the theorem by itself, but the process by which we modified our definitions to get the theorem is what is interesting, because these are interesting things to do. So let me now go towards that. Sorry, so first thing is I'm overshooting the time a little bit. So if the organizers don't mind, I will overshoot by some 5-10 minutes. Is that okay?
Yes, sir, it is perfect.
Okay. And also I'm going a little fast towards the end because I just want to come to the end. Okay, so here are some examples. We need to, so what we'll do is we will be mainly interested in curves coming from R2 because that is our starting point. And so what we really need to, we will be doing is we will only be drawing the real pictures because there's no way we can draw the complex pictures. It's just too complicated. And anyway, it's in R4, so that we cannot do. And we can at the best say that after some continuous transformations, it looks like so and so. But anyway, that's more complicated situation. We'll not get into that. Having said that, however, this theorem requires you to work in CP2. So what we will do is we will draw real pictures, but we need to algebraically look at the underlying complex points. So we actually need to look at them and we will mention them also. Okay, so let's start with the situation we have already done so far, which is parabola and a line. But in fact, instead of parabola, you can use any conic. So you can use a circle, ellipse, hyperbola, and a line. And you will see a similar situation. Either the line cuts it in 2 points, or if the line is tangential, it will cut it in exactly 1 point. Or in some situations, the line doesn't seem to cut it at all. In that case, either there is a complex solution. So for example, if I have a ellipse and if I line far away from it, there'll be a complex solution between them. The points of intersection are in the complex plane. And in some cases, it's asymptotic, like hyperbola and the asymptote. They don't seem to meet, but they meet at infinity. So the total intersection number is always 2. Is simply always 2 if we work in the complex projective plane and use multiplicities. So I didn't mention that. Okay, let me just orally say it. So, and use multiplicities here. Let's look at two ellipses, degree 2. So the theorem says that it should have 4. And indeed, you can see there are 4 points here. Of course, if you move the ellipses a little bit, then you get here, and then there's a tangential intersection here, and several things can go wrong. Here, there are complex solutions, so you're not seeing them. And here, there's a tangential intersection, so maybe here, I forgot to calculate the intersection multiplicities. Probably it has, yeah, okay, I'm not very sure. So here, what the yeah, maybe this also has some complex, so 2 more complex points at infinity. But whatever it is, the intersection number is always 4. But we still see a situation where the full intersection number is achieved. And these are the sort of the other situations where you have to go back to projective, or you have to go to the projective space or some tangential multiplicity to account for, get the full 4. A similar situation is 2 circles. But here something peculiar happens. The intersection number never reaches the maximum that you should get. two circles are degree 2, so Bezos theorem would say it should be 4. And we know that it need not be 4 in certain situations, but in the case of circles, it's never 4. It's either 2 or 0, or maybe 1. I mean, so, but that is the intersection multiplicity. Yeah, so here also I think it's 1. Intersection multiplicity is 2 actually. So why is it that you never get the situation where the intersection number is 4? So for that, you have to go back to the points at infinity. And if you do that, let's take a typical circle. Here's your typical circle. Homogenize it. This is your homogenized equation. Put z equal to 0. So I put z equal to 0 here. What do I get? I get capital X square plus capital Y square is equal to 0. And now z is 0. I'm in the complex projective. I'm in the projective space. In fact, complex projective space. So y cannot be 0, x cannot be 0. So I put one of them 1. So I put x equal to 1, and then you see that y has to be plus or minus I. But something interesting has happened. First is that the point at infinity, even though we started with an equation having real coefficient, the point at infinity has suddenly become complex. But the other interesting thing is that it's independent of a, b, and little r. And what that tells you is that all circles in R2, in fact, have the same 2 points at infinity, and that's why you are never seeing full intersection number 4 here. You will only see 2, because all circles will have these points at infinity, and they will probably meet. I think they will meet. One has to calculate the intersection multiplicity at the infinity point, and they will meet there tangentially. So it is because they all have this common point at infinity and they seem to meet there tangentially. Therefore, that's why we will never see the intersection number 4 for 2 circles. Okay, so that's about Bezos theorem. Moving on, and I'm now towards the end of my lecture, 5 more minutes, hopefully. We get some interesting things out of this. So over CP2, all these real smooth conic sections like circles, ellipses, smooth, I say because I think 2 lines intersecting probably is also, I don't remember, is it also called a conic section perhaps? So to avoid that, I just add the word smooth here. So all these real smooth conic sections, circles, ellipses, parabolas, hyperbolas, all these things are in some sense up to a linear change of coordinates, they are actually equivalent. So to illustrate that, let's look at some specific examples. So here's an example of your, circles are anyway degenerate ellipses, or a special class of ellipses. And if you do a linear change of coordinates, you can go from circle to ellipse. So here you have a circle, and here you have a parabola, and here you have a hyperbola. Now you'll notice that this equation are very similar. But over real numbers, they are not. But over complex numbers, replacing y by a scalar multiple, namely iy. Replace y by iy. So scaling up one coordinate by a complex number, namely the square root of -1, will go from this equation to this equation. So really, over complex numbers, these 2 equations are really equivalent. And you will see that this hyperbola, you can also think of it as, this is also an example of hyperbola. And these 2 are linearly equivalent because replace x minus y and x plus y by x and y. So replace x plus y by x and x minus y by y, or one of these linear change of coordinates will transform this hyperbola to this hyperbola. And this hyperbola is looking exactly like this parabola. I mean, it's just the variables have been permuted, that's all. So really, in CP2, they are all just change of variables and they all become equivalent. I mean, you can go from one to the other. So why are they different when you're not in CP2? Why are the real ordinary points different? And basically that comes by looking at the points at infinity. Circle has 2 complex, or ellipses have 2 complex points at infinity. For circles, it's exactly these 2 points at infinity. But these are complex, they are not real. A parabola defined over real numbers will always have 1 real point at infinity. And that's why it is different from a circle. I mean, of course, we know it's different from a circle, but now we are saying that even though they are equivalent over CP2, the reason why they are not equivalent over our real space, or usual real space, is that they have, first of all, they have only one point, and the other is that that point is a real point. And the hyperbola is again characterized by the condition that it has two real points at infinity. So this had two complex points at infinity. This one has two real points at infinity. And that is sort of telling you why they are different. But at the same time, we also can see that they are all actually similar. There's not really much difference between them when you go to CP2. Yes?
Does the two, for the circle, does the 2 points, that is 1 plus minus I 0, that is the 2 points at infinity, are you saying that it accounts for the 2 missing points? Like it should be 4 according to Bezos Theorem.
Yes, it accounts for 2 missing points, and I think they meet tangentially there. So because they meet tangentially, the intersection no, not tangentially. They will probably meet at both the points tangentially. So that's why I think
circles have this property. So
yes. So that's why
all of they intersect.
They will all intersect those 2 points, and depending on the kind of circle you have, they may intersect tangentially at least one of those points, or maybe both. So it depends on if you have 2 concentric circles, most likely they meet tangentially at both the points at infinity. And if you don't have concentric, then probably they meet transversally at the 2 points at infinity. I think that's what is happening. Yeah. Okay, so moving on, wait a minute. I think I don't have much here. So 17. Yeah, I think I just have 1 or 2 slides now. So I'll just give a general fact. This is the last thing. Complex projective curves. So now I've dropped the word plane projective curves here. So in fact, one can talk about curves in R3, R4, and similarly C3, C4 also. It's a little more complicated. So I don't want to, because basically if you are in R3, to define a curve, you need more than one equation. You will need 2 or 3. So it's not, one has to be a little more precise, and so it's a little more technical. So let's just ignore those technicalities for the time being, and just take it on faith that one can give a definition. So complex projective curves with one added condition of being smooth. So they shouldn't look like this y square minus x cube, which was something like this. So there was a sharp point here, or they shouldn't look like this. So if you don't allow these kind of examples, then actually your locus will always have a smooth appearance. And so these, if you put this smoothness condition, so that's you can make this precise using partial derivatives and all that. So there's a precise algebraic condition for that. I'll not get into that, but let's assume that one can do that. So if you do that, then topologically one can show, and this was the question somebody was asking earlier, they'll either look like this sphere. So all your conics, they are all equivalent over complex projective space, and they will all look like a sphere. And so your parabola, complex parabola, will be missing a point at infinity, so it will be a sphere minus a point at infinity. But all your conics will, smooth conics will look like a sphere. These smooth cubic, so I wrote down one such equation, probably something like y square is equal to x into x minus a into x minus b, something like that, where a and b are not 0, a not equal to b and not equal to 0, such things. So if you have distinct roots here, then something like this, if you start with, then what you get is a smooth cubic, and one can prove that its underlying complex projective structure, the underlying complex projective curve has this, after some continuous transformations, looks like the torus. This is your usual donut or vada shaped thing, medu vada shaped thing. And it's also called an elliptic curve. So if you hear this word in some other context, it's basically a curve which comes from something like this. And then more complicated looking curves will have more complicated shapes, but one can show that they'll all look like one of these types only. So which is multi-torus. So a torus with one more handle, and this is a torus with 2 handles, and so there are. So the number of holes is called the genus. So that's your sphere, torus, and two torus, 3 torus. And here the genus is 0, genus is 1, genus is 2, genus is 3. So genus is just a word, just like in biology, to tell you what type of surface is it. So one can show that all complex projective curves, which are smooth, will look like this. I forgot to add connected, so it should also be connected. So you can have a disjoint union of 2 curves also. So I forgot to add that. Okay, let's just add that. And so this is my last slide here, and I'll end with this. Sorry, I took a little bit more time. So all this is turns out it's related to interesting number theoretic fact. So I'll give two facts. One is an easy fact. So the easy fact states the following: all rational points of a rationally defined conic. So here rational conic means that a conic which is defined over rational numbers, so whose coefficients come from rational numbers. And in fact, all our examples that we wrote had integer coefficients, so they are all rational conics, for example. And now I'm interested in rational points, means points which have rational coordinates. Assuming they have at least one rational point, so you can give examples where there are no rational points also. I think something like x squared plus y squared is equal to 3. You can probably show that it has no rational points. So assuming it has at least one rational point can be described. So all the rational points of this rational conic can be described in terms of a single parameter. So rather than describe that, make this precise, let me say what we are doing. So this is your rational point P here. And to describe all the other rational points here, I'll take a typical rational point Q here, and I'll fix one line L, which is also rational. So this is also a rational line. Rational line means it has rational coefficients. So ax plus by plus c is equal to 0, where a, b, c are rational, if you like. So take a rational point and take a rational line, and now take a typical rational point here and join these two. Bezos theorem says that this line will not intersect. We don't really need Bezos theorem, but okay, Bezos theorem in particular says that this line will not intersect any further on this conic, and it will go and intersect this line exactly in one place, well, almost all the time, except if this line happens to be parallel to this, which might happen if your Q maybe reached somewhere here or something, and then maybe you might see something parallel. But if you are willing to go to infinity, then even that can be taken care of. So it will go and hit this line at a unique point Q prime. So that we will call as projection from P. So I'm projecting this point Q from the point P. And where is Q going? It's going to this point Q prime. So this projection is what we'll define, because what one can do is we can show that whatever the coordinates of this are, you can write down these coordinates explicitly in terms of these coordinates using rational expressions. Because this line has slope rational, and this is rational, this is rational. So this line has slope rational number. And so you can really solve for this point, and everything will be a very nice rational number, which can be determined by just solving linear equations. And maybe there are some denominators. So you can actually explicitly, so just simply look at all the rational points on this line, and they will be in 1-1 correspondence with rational points of the conic. And so therefore, rational points on this line are like rational points on this conic. And so you can, that's what I mean by saying they can be described in terms of single parameter. And in particular, for example, if you choose a unit circle here, circle of radius 1 with center origin, you will recover your Pythagorean triplets. If you do it carefully through a particular line, you'll get rational points, and you have to sort of clear off the denominators, and you'll get your Pythagorean triplets because they are x squared plus y squared is equal to z squared, but that's really x squared plus y squared is equal to 1. I mean, it's the whatever, x over z whole square plus y over z whole square is equal to 1. So it's really coming from the rational line. So what this tells you is that rational conics, conics over rational numbers have plenty of rational points. If they have one rational point, then they have in fact infinitely many of them. 1-1 correspondence with points on this line. And now here's so this is the last thing, and I'll stop here. There's a hard fact, which is a remarkable theorem. For example, you can apply it to a curve like this: xn plus yn is equal to 1. Or which is related to the Fermat equation, xn plus in. So if you are interested in integer solutions of this, what this theorem, it does not prove Fermat's last theorem, but what it does is it tells you that there are only finitely many solutions for n large. What is the statement? It says that a rationally defined projective curve. So now you have to look at projective curve, and you have to talk about its genus. And the only way to talk about its genus is to go to the complex points. So you have a curve defined using rational coefficients like this one here. Look at the projectivization, look at its rational, look at its complex points, look at its genus. If the genus is greater than or equal to 2, and one can show in this case by some explicit calculations that a genus is greater than or equal to 2, then it has only finitely many rational points. And so you can come back and say that there are only finitely many solutions for this with no common factor. There are only finitely many integer solutions also. So it's a remarkable theorem. It does not prove Fermat's last theorem, but it gives an almost proof in the sense that it tells you that for any n, there are only finitely many solutions. This is a very difficult theorem, very advanced theorem. But what I want to highlight is that even to think of such a theorem being possible requires you to first expand your domain of knowledge and go from just looking at ordinary curves to projective curves, complex projective curves, talk about their topological nature, and then of course this theorem itself is some quite difficult theorem. So that's another thing altogether. Okay, thank you. So sorry I took more than 15 minutes extra. Thanks for the time. I'll stop here.
No problem. Thank you very much.
Okay. You're welcome.
So,
yeah.
Do you have any questions, participants?
Yeah, that is your genus here. So genus greater than or equal to 2 was here.
So,
yeah.
Could you suggest some resources on algebraic geometry?
So you want to, if you want to read some basic introductory stuff on this, okay, so let me write some references here. I don't know if I can give you precise references, but I can sort of suggest from which then you can figure out the actual references. So one is, I think it's, the author is Miles Reed. I don't know the spelling, R-I-E-D or R-E-I-D, I don't remember. And the title should be something like Introduction to Algebraic Geometry, maybe. There's a similar book by William Fulton.
Sir, what basic prerequisites does this book require?
Some algebra. So abstract algebra. So a few courses in abstract algebra. Basically, you need to know about rings and vector spaces and fields, and a little bit, rings, especially ring theory, a little bit more. So but of course, anybody who wants to learn about rings and vector spaces and fields will initially have to learn about groups and linear algebra also. So matrices and all those things. So that is assumed. And after that, you have to read about rings. So some commutative algebra and perhaps a little bit of, I'm not sure, a little bit of topology, maybe some basic point set topology. So there's also this, I think this book also pretty much, this is maybe some algebraic curves. I'm not very sure. I'll just say the prerequisites shortly, just 1 minute. And there's also this book by Keith Kendig. And again, I'm not very sure of, I think it's something similar, some introduction to algebraic geometry or something like that. And so prerequisites would be basically some courses in algebra. So fields, rings, quite a bit of rings is needed and a little bit of topology. Depending on what flavor. So there are different flavors for algebraic geometry. There's a more analytic flavor, and if you want to do that, then you have to learn about complex analysis and differential geometry also. So this is what I would suggest. And the number theoretic applications tend to be a little more advanced. Oh, that reminds me. There is, however, one book. I think it's Silverman and Tate. Maybe Rational Points on Elliptic Curves. I'm not very sure of the title. perhaps rational points on elliptic curves. So that all these number theoretic applications, a little bit more is there on that. And also it introduces in a very elementary way. I read this book very, very long ago, so I don't remember now. That's more than 20, 30 years ago, so 25 years ago maybe. So I don't remember now, but I think something like this is. So depending on the different books, they will have different prerequisites, but I would say broadly speaking, these are the prerequisites: algebra and topology. Topology of first course. So just definitely, I don't even know you really. Yeah, I guess you need, because a little bit of understanding of topology helps. Compactness, connectedness, those kind of things. Open sets, closed sets, all those things. Yeah. Any other questions? Okay. Sir, could you suggest any source? Yeah, okay. I think I've done that. Is there one more question? Oh yeah, okay, feel free to ask any questions. Yes.
Sir, Atharva Mahajan asks, can you give a rigorous definition for smooth?
Oh, I see. Okay. Yeah, okay, let's try that. So where was I? Yeah. So smooth in a very general context is more technical, but in the context of in the context of a plane algebraic curve, it's much easier. So we will say f xy equals to 0 defines a smooth curve at a point. So it's a local condition. So I mean, what is happening far away really has no effect on B if, all right. So basically just look at the partials. So del f by del x, and so let's call this point P as P, and del f by del y at P is not equal to 0, 0. Okay, so I should have just used this. Meaning that both of them are not simultaneously 0. At least one of the partials is non-zero. So this is your definition of a smooth curve at a point A, at a point P, A, B on the curve. So this point is So that's important on the curve. So you have this equation, and then you do this. So for example, if you look at y square minus x cube is equal to 0, then take the point P is equal to 0, 0. So this is your f. Then you will see that fx, the partial derivative, and fy, the partial derivatives at the point P are actually, so it's 3x square and y at 0, 0, which is 0, 0. So therefore, this is not smooth. And that is your picture that you have here. Oops, sorry. I mean, it's okay. I was almost there. The same thing. And so this is your point here. And this is looking like a sharp point in this neighborhood. That's your origin. And one of the partials, both the partials are vanishing. That seems somehow is a problem. Whereas if you take any other point on this curve, I mean, some, say 1, 1 or something, you will see that at least one of the partials will be non-zero. In fact, at 1, 1, both the partials are non-zero because you have the explicit formula for the partials right here. Maybe I forgot the minus sign here. So there's a minus here. So minus 3x. So that is your definition of a smooth curve at a point. And you say the curve is smooth if it is smooth at every point. So for a plane curve, that's an easy definition. The problem with non-plane curves, non-planar curves is that even the definition of curve is more complicated. So then defining smoothness also becomes correspondingly quite complicated. I mean, essentially, you will see that you are not able to define the tangent line here because if you go back to your definition of what is a tangent line, it will be something like fx times x minus a plus fy times y minus b at this point. That is equal to 0. That's the equation of the tangent line. And you are seeing that you're not able to define the tangent line here. Intuitively, that's another way of looking at it. No tangent line.
So if there are no questions, I think we can start.
Okay.
Okay, sir. Thank you, sir.